Okay, so if you're an engineer, maybe a designer, and you're working with the really, really squishy stuff, like specialized rubber, maybe some complex polymers, or even biological tissues, you hit this um, unique computational brick wall pretty fast. We're talking materials that are almost incompressible. Their Poisson ratio, that's a new, it gets really close to the limit, point 0.5.
Right, and that point 0.5 limit, it's a real headache for traditional computational modeling.
Yeah.
Your standard finite element method, the workhorse for, so many simulations, it just kind of falls apart when you try to model these materials. It's a failure mode called volume locking. Pretty notorious, actually.
And locking isn't just like an annoyance. It completely tanks the simulation.
Oh,
The little
right.
pieces in your model, the elements, they just stop deforming properly. They get weirdly stiff.
Yeah.
And the stresses you calculate, which are often the whole point, they're
Yeah.
completely off. Sometimes they just mathematically shoot towards infinity. Now, if you're designing, say, a medical device or maybe a component for soft robotics, that's just, oh, well, it's not acceptable.
Exactly. It's completely unacceptable. What we really need is a method that gives us what we call uniform stability, meaning the stability holds up whether your Poisson ratio is, say, zero point 0.3, which is pretty compressible, or if it's pushed right to the edge like 0.499999, nearly incompressible.
Okay, let's definitely unpack this because today we're doing a deep dive into what sounds like a novel solution, a potential way out of this volume locking trap. We're looking at a really interesting paper that details a primal double hybrid finite element formulation. It's called DHMRH. And
Mhm.
our mission really is to figure out how this method, this DHM iode, uses some quite specialized math built around specifically these L-torn-2 spaces to get really accurate, stable results for 3D elasticity, no matter how squishy that material is.
That's right. It essentially comes from trying to fix some really fundamental flaws in the methods people were using before.
Okay, so let's start there then. Before this double hybrid approach came along, what was the standard playbook for trying to simulate these nearly incompressible solids? And, where did those methods fall short?
Well, the main strategy people used and still use a lot is the mixed formulation. So instead of just solving for displacement, you add another variable you solve for independently. Usually that's pressure, sometimes stress, and the elements everyone knows here are the Taylor-Hood family, like PA11. They're popular because if you design them right, they meet these crucial stability criteria. The LBB condition, ladies in the sky, Babu Subrezzi. That basically ensures they don't completely lock up.
Okay, so they kind of solved the locking problem, the stability part, but it sounds like there was a trade-off. A new problem popped up.
Exactly, you hit it. The required continuity of that extra pressure field became the Achilles heel. See, tailhood elements in force was called H-1 continuity. That means the pressure has to be smooth, continuous everywhere, across element boundaries. But that assumption just doesn't match reality when you're modeling, say, non-homogeneous materials. Like imagine a soft layer glued to a stiff layer.
Right. Because in the real thing, the stress and therefore the pressure, it should jump. It should be discontinuous right at that boundary between the materials. But Taylor-Hood smooths it out.
It forces a smooth transition, yeah.
Ah,
And that forced smoothness creates numerical noise. Specifically, you get these things called spurious oscillations right at the material interfaces. So even if the overall simulation looks stable, your local stress calculations right where you might care most, like at an interface, they can be inaccurate. And well, that's where hybrid methods started to come in, kind of like pragmatic revolutionaries, as you said.
pragmatic revolutionaries. I like that. So the core idea for hybrid methods is they relax that strict connection between elements.
That's the fundamental shift, yes. Hybrid methods let the elements uh, communicate a bit more loosely, you could say. They don't demand strict continuity across element faces for everything. Instead, they enforce it weakly. And they do this using special variables called Lagrange multipliers, which only exist on the boundaries on the faces between elements, not throughout the whole element volume.
Okay, now we're getting to the really interesting part. The architecture of this DHM method, it starts with a very specific choice for the displacement field space. Why start there? Why instead of the usual H-1 space we often use for displacements? How is that key to tackling locking?
It's really about what text-dive functions are good at. They naturally deal with flux, or, flow. So if you think about the displacement field like it's describing a flow of material through the volume, choosing X-dive automatically ensures one crucial thing. The component of displacement that goes normal to an element's face, straight across it, is continuous. That continuity is just baked into the mathematical properties of the text dive space itself. And that's huge. for preventing unwanted volume changes, making sure the flow across boundaries is consistent.
Ah, okay. So the locking resistance, that normal displacement continuity, is sort of built in from the start just by choosing the right mathematical tool. But displacement isn't just a normal, right? There's also the tangential part, movement along the face. What about that?
Right, that still needs to be handled. The tangential continuity isn't guaranteed by text tacte. So this brings us to the first hybridization step in this method. We enforce that tangential continuity weakly using a Lagrange multiplier, just like we discussed with hybrid methods generally.
Okay, and this first multiplier, what does it physically represent?
Good question. It ends up being associated with the tangential traction. That's basically the shear stress acting on the element faces. So we're enforcing tangential displacement continuity using a variable related to shear stress. At this point, technically, we have what's called a semi-hybrid formulation. We've handled continuity, but we haven't quite gotten to the big computational payoff yet.
And that requires the really novel bit, the double hybridization. Okay, walk me through that second step. It sounds complex.
It is a clever move. We take the thing we just introduced, that shear stress variable, the tangential traction multiplier, and we apply hybridization again, but this time to that multiplier itself. It might seem a bit counterintuitive, hybridizing a multiplier, but doing this introduces a second Lagrange multiplier, and this final second multiplier.
Yeah.
Turns out to be physically associated with the tangent displacement itself directly.
Okay, that sounds like some serious mathematical footwork. But what's the game? What is doing it in two steps by us, computationally or physically? Why not just one step?
Locality. That's what it buys us. By putting in that second layer of hybridization, the shear component of the traction field, the thing we introduced in the first step, it becomes mathematically trapped, you could say. It becomes entirely determined by variables that live only within that single element. It doesn't directly connect to the neighbors anymore in the final system. And because it's now purely local, an internal degree of freedom for the element, we can eliminate it mathematically before we even assemble the big global system of equations for the whole structure.
Ah, so that's the key. This double step enables the famous computational trick, static condensation. You're basically doing a bunch of the maths locally, shrinking the problem element by element, before you tackle the giant global puzzle.
Precisely. And it drastically cuts down the number of unknowns, the size of the matrix, in that final global system you have to solve. Huge computational savings. Plus, it has major benefits for stability. For materials that are just compressible, not incompressible, doing this static condensation actually gives you back a perfectly symmetric, positive, definite matrix. That's the gold standard for numerical solvers, easier and faster to solve reliably.
And even for the really tricky incompressible limit, $1.55, where you usually end up with a more difficult saddle point problem, the paper suggests this method still makes things much more stable than older semi-hybrid methods.
Yes, significantly more stable. And here's a really neat detail. After you do all that static condensation for the purely incompressible case, the final system you solve is governed by just one Lagrange multiplier per element. And that single multiplier represents the mean pressure within that element. So you've essentially boiled down the complex physics of maintaining constant volume within each element to a single constraint enforced by this one pressure value per element.
Okay, the theory sounds incredibly robust, airtight almost. But let's look at the proof. How did the researchers actually test this? They put DHMG through some classic, pretty tough benchmark tests, right?
They did. They used several standard benchmarks designed to expose weaknesses like locking or problems with stress discontinuities. Let's start with one called the uniform stretch test. This one's a great challenge for methods like Taylor-Hood that enforce continuity everywhere. They set up a cube made of two different material layers, different stiffnesses, E11, E2, or 2 but critically, both layers were perfectly incompressible, 1,555 cents. Now, mathematically, we know the exact analytical solution for the stress in this case, and it should have a sharp jump, a discontinuity right at the boundary between the layers.
And the result, how did DHM do?
It nailed it. The DHM voice formulation reproduced the exact analytical solution perfectly for both stresses and displacements. And here's the kicker. It did this using just two elements, the absolute coarsest mesh possible, just one element for each layer. That's a huge deal, because methods like Taylor-Hood, with their continuous pressure fields, they can't capture that sharp jump exactly. They can only get closer and closer as you use more and more elements, as you refine the mesh. DHM voice gets the exact discontinuity on the crudest mesh. That really shows the power of its stress representation.
Wow, okay. That's pretty compelling evidence against that forced pressure continuity flaw in the older methods. But the ultimate test is really about the locking freedom itself. So that brings us to the 3D cantilever beam benchmark. load it under shear, right, and test it across the whole range of compressibility.
Exactly. They really pushed it on this one. And this test demonstrated what we call uniform convergence. The method achieved the best possible convergence rates typically. That's order K plus 80 on improvement for displacement error and order actia dollars for pressure and stress error as you refine the mesh. And crucially, these rates were completely independent of the Poisson ratio. It didn't matter if one was 0.3, 0.49, or 0.4999. The convergence was just as good. They pushed it right up to the limit and even passed it to new dollars of 5.5.
And what happened at that exact incompressible point, $1.55?
Perfect behavior. For newer dollars and 5.5, they got a displacement field that was truly divergence-free, meaning, mathematically, volume was conserved perfectly down to the limits of the computer's precision, even on coarse meshes. This is really the definitive proof that it solves the volume locking problem. It just doesn't happen with this method.
Okay, locking freedom, check. Stress discontinuities, check. Now, what about the practical side, the efficiency? That static condensation promised big computation savings. Did they show that off too? Maybe with the Cook's membrane test? That's another classic locking benchmark, isn't it? Known for shear and bending issues.
Yes, Cook's membrane is a tough one, especially for locking. And DHM delivered locking-free solutions even with the simplest version, the lowest order approximation. But you're right, the efficiency numbers were really impressive. The static condensation really shone here. In the best case scenario they tested, which was using a high order approximation, KC $4, on a nice structured mesh made of hexahedra like cubes, the condensation step slashed the number of global degrees of freedom, get this, by up to 90%.
90%. Okay,
Yeah.
cutting the size of the problem you actually have to solve globally by nearly a factor of 10.
Right.
That's potentially transformative for large, complex simulations. That's the payoff for all that careful mathematical design.
Absolutely. It's a huge win.
All right, so it performs brilliantly on these, let's say, controlled experiments, these benchmarks with nice shapes. But we have to ask, how does this super specialized method handle the messiness of a complex real-world geometry? The paper mentions testing it on a structural hull under pressure using an unstructured mesh made of tetrahedra, right?
That's right. This was the reality check. They modeled a quarter section of this whole shape using these complex, unstructured tetrahedral elements, and they compared DHM directly against Taylor-Hood elements for the same problem.
Now, hang on. A tetrahedral mesh, that's not ideal for this method, is it? Because DHMG puts those Lagrange multipliers on the faces of the elements. And tetrahedra, compared to cubes, have a lot more faces relative to their volume.
You've nailed the issue. The efficiency of DHMH, and especially the benefit from condensation, is definitely linked to the element shape. Tetrahedral meshes inherently have a high surface area to volume ratio, meaning lots of faces. So the number of raw degrees of freedom, before you even do the condensation, was significantly higher for DHMB to POWs in this test compared to Taylor-Hood. And this is important. Even after they applied static condensation, the total number of degrees of freedom that needed to be solved globally was still lower for the Taylor-Hood simulation in this specific case, with this complex, unstructured geometry.
Wait a second. If the big computational selling point is the static condensation reducing the problem size, but for a realistic, messy geometry, the older Taylor-Hood method actually ends up being cheaper computationally. What's the takeaway here? Is DHM gestury only practical if you can use nice structured brick meshes?
That's a really fair question, and it does highlight the practical trade-offs when you push numerical methods to their limits on complex problems. So yes, for this specific setup unstructured TEP mesh, Taylor-Hood had fewer final DOFs. However, the DHM results were still robustly locking free, which isn't always guaranteed for Taylor-Hood under extreme conditions. And importantly, the paper notes that the DHM solutions produced smoother solution fields.
Smoother fields, meaning less of that noisy, spurious oscillation stuff we talked about earlier, especially near material interfaces or complex features.
Precisely.
Sure.
So it confirms that even if the raw computational costs might be higher for certain unstructured geometries, the quality and reliability of the solution, that guaranteed stability, the better local stress accuracy, the lack of pressure wiggles, those remain significant advantages. That advantage might justify the higher DOF count, especially if you're doing simulations where accurate stress prediction, maybe for failure analysis near tricky features, is absolutely critical. It basically proved the method's robustness holds up in complex 3D, even if it doesn't automatically win on pure speed for every single mesh type.
Okay, that makes sense. It provides that necessary balance. It's a method that's mathematically superior, especially for stability and stress accuracy, but its practical computational efficiency can depend on the geometry and mesh type you're using. But the accuracy benefits seem absolute.
That really is the core takeaway, yes. DHM, Vectex, gives you a scheme that works uniformly well, stable, convergent, no matter the Poisson ratio. True locking freedom. It allows for accurate local stress calculation, which is a big leg up on conforming methods like Taylorhood. And thanks to that clever double hybridization enabling static condensation, it often achieves really competitive, sometimes superior performance, particularly for nearly incompressible cases and often unstructured meshes. And it's worth mentioning they implemented this in an open source platform called NeoPZ, written in C++ West, so the tools are actually out there for people to potentially use and build upon.
All right, so here's where we leave you, the listener, to think about this a bit more. We heard that for perfectly incompressible materials, when U is exactly zero point 0.5, this whole complex DHM Lauro scheme, after all the elegant maths and condensation, boils down to enforcing just a single mean pressure constraint within each element. So if you can essentially capture the core physics of how these incredibly soft, squishy solids deform by managing just this one pressure value per element, how might that kind of localized, simplified constraint revolutionize the way we design things like soft robots or biomimetic devices? Applications where getting precise, controlled, complex deformation is absolutely everything, something to mull over.